Good afternoon, everyone. Today I wanted to catch us up on the discussion of, I believe it was February 25th. It was Monday the 25th, and some of the things that we talked about in lecture on that day. So the two main points were protein gels, so SDS Page versus native page, and then I wanted to follow up with a discussion of molecular scissors. So go ahead and please pay attention. So whenever we're looking at SDS page versus native page, what we need to go ahead and first square away is, what does page stand for? That stands for polyacrylamide gel electrophoresis. Now the difference between the phoresis, the difference between these is what you're doing to the proteins that you're analyzing with this technique. So SDS page, what you're doing is you are going to denature a protein. So this is also known as denaturing conditions. And what you're doing, naturing, is you are going to take a 3D folded protein, and you're going to heat it up, and you're going to add something like DTT. DTT, or beta-mercaptoethanol, beta ME. These are substances that will break disulfide bonds. The last thing that you're going to do in SDS page is you're going to add SDS, which stands for sodium dodecyl sulfate. Sodium DODECYL sulfate. And what you're doing with sodium dodecyl sulfate is you're adding a uniform negative charge across the protein. So after you've added heat, DTT, or beta-mercaptoethanol, and SDS, what you're going to do is you're going to take this three-dimensional protein here that, it might have an intrinsic charge, or it might have surface exposed like arginines or lysines that have positive charges, as well as some aspartic acid and glutamic acids. You are going to unfold that protein, and you're going to make a uniform molecule, and that uniform molecule has negative charges all along it. Those negative charges are coming from the SDS that you've added to that mixture. Okay, so what you're doing then is you're able to compare proteins of different sizes, and you've given them all the common denominator of having an overall negative charge. And so what that means is smaller proteins are going to be more influenced by any sort of electric current that you run through an SDS page. So here's an example of an SDS page. You have a negative charge up here, a positive charge down here, and the larger the protein is, the slower it's going to move. The smaller the protein is, the faster it's going to move. So let's go ahead and just use those two examples, and this would be 160 kilodaltons, and this would be 20 kilodaltons. So that smaller protein migrates through this polyacrylamide matrix at a much faster rate. Now, in an alternative setting, you have native page. Native doesn't stand for anything. That's just a matter of looking at, well, non-denaturing conditions. So what happens whenever you have a protein gel and you don't add those uniform negative charges? You don't disrupt any disulfide bonds, and instead you just load maybe a protein, like let's take this combination from here. In an SDS page, we saw 2 bands. In a native page, you might see 1 band. Why would you see 1 band? Well, the reason for that is because one reason for that is you could be looking at a dimer. So the great thing about SDS page versus native page is for comparison. So if you do a native page and you see 1 band in there, and then you subject the same sample to SDS page analysis, 1 band in that native page, and you see 2 bands in that SDS page, well, then you'd be able to say, well, I'm working with a dimer, or at least a dimer that is probably 180 kilodaltons. In all likelihood, it's a dimer that's 180 kilodaltons. So that's one of the values for SDS page versus native page. you can do this comparison. Larger proteins migrate at a slower rate than the small proteins. Small proteins migrate through that matrix at a fairly high rate. So the last thing that I wanted to talk about here were molecular scissors. And molecular scissors give you kind of a way of cutting a polypeptide, cutting a protein, and seeing how many products it results in. What you need to know are a total of 3 different enzymes and 1 chemical. So the 3 enzymes are trypsin, chymotrypsin, and elastase. These cut peptide bonds. Cyanogen bromide is also a treatment that is going to cut a polypeptide or a peptide bond, but it's a chemical compound. Now, what makes these different from one another is what they cut after. So if I gave you a polypeptide, that's what I would want you to be able to answer. So trypsin is going to cuts after positive residues. Now, chymotrypsin cuts after, so I'm going to circle, chymotrypsin cuts after bulky hydrophobic residues. And elastase is going to cut after smaller residues. And an example of that would be something like alanine and glycine, ANG. It will also cut after other residues. In your PowerPoint presentation, I showed you more specifically those specific substrates. Cyanogen bromide is going to cut after methionine. Now, for these enzymes, the one thing that you need to keep in mind is an exception to the rule. These are going to cut after positively charged residues, bulky hydrophobic residues, and after smaller residues. However, if there is a proline, so for instance, if we had a polypeptide that was arginine and proline, okay, and we subjected that tripeptide to trypsin, trypsin will cut here, so after this arginine, but not after this arginine. And the reason for that is that this arginine has a proline that follows it. Okay. Now, if we took something like chymotrypsin and we put WRRP, what is chymotrypsin going to do? Chymotrypsin is going to cut after a bulky hydrophobic residue like tryptophan. Is it going to cut after arginine? No, it is not. That is unique, or that's more common for trypsin. Will chymotrypsin cut after this arginine that precedes the proline? No, it will not. Okay, so chymotrypsin is going to seek out a bulky hydrophobic residue. Elastase is going to look for smaller residues, like ARP, a peptide for the American Association, or the Association of American Retired Peoples. Anyway, where is elastase going to cut? It's going to cut here, and it's going to cut here. It's not going to cut here, not because there's a proline there, but just because it's not going to cut after that positively charged residue. Cyanogen bromide is going to cut after an M, so it would cut something like MA, so cyanogen bromide would cut that, and ML. It will cut there, so ML, it will cut that. So it's important to know these rules. What are the residues that these different proteins are looking for, and what are they going to cut after? In the next video, I'm going to go through an example of basically using this information to map a polypeptide. What does this polypeptide look like whenever you've got all the amino acids distributed? What are the products that you can generate, and so forth? All right, well, thank you very much for watching. I hope this clarified some information for you.